So this is for solutions to the homework on energy problem, exercise 11.3 from the Real World Physics textbook. On a good suggestion of one of the students, I'm going to present the answers to all the questions first. So these are the answers. You can pause the video and look at the answers in your own time to see if they got correct answers. And then I'm going to take a look at the solutions on all the problems so that you can review the problems in your own time if you need to. But these are the answers to the questions. So I'm going to start the solutions now. So for question number one is asking us to take a look at something like, so particle of mass 20 is thrown upwards to a vertical height of 60 meters. We're looking to find the increase, 600 meters. We're looking to find its increase in potential energy. So if I draw it out, it's fairly simple. Particle starts over here and it's thrown up and it reaches height of 600 meters. So that's our H. So potential energy EP is equal to mgh. We have all the values given, so we can now just substitute into the equation because we know what mass is and we know what the height is. So in this case, we end up with 20 multiplied by 9.8 multiplied by 600, and the value is 117,600, 117,600, and joules. So that's the answer to the first question. Number two is quite similar. So for question number two, we want to look at how far above the surface must a mass be raised so that its potential energy is increased by 4,000 joules. So take a look again. We're starting from the ground level. Particle is raised up until some point over here. It reaches height h, and we know that it has some potential energy equal to 4,000 joules. So we know that EP mg h, so from that height is equal to EP divided by mg, and that goes to 4,000 divided by 4 times 9.8, and that turns into the height of 102.04 meters. So that's question number two. Moving on to question number three. So in question number three, we're looking at a stone dropped from some height. We're looking to find its kinetic energy. So this I'll just draw it out a little bit more in detail. So the stone comes from over here. It has some potential energy because it's at a height h. And it will have some kinetic energy, but that value of kinetic energy is equal to 0 because obviously the stone doesn't have any speed. And right here, just before it collides with the ground, well, it collides in this drawing, but let's draw the ground first, and now we can draw the stone. At this time, all of the potential energy of the stone turns into kinetic energy. So in this case, EP will be equal to 0, and EK will have some value. So if we write down, let's call them 1, and let's call these potential energies 2's. So if we write the principle of conservation of mechanical energy, we get that EP1 plus EK1 is equal to EP2 so that turns into EP1 has some value, mgh, EK plus 0 is equal to that 0, and that's mv squared plus over 2 mv squared. Now, finally, we can solve our equation. solve our equation to find its kinetic energy and the speed. So first of all, useful thing to note is that kinetic energy is this, and kinetic energy will be equal to the same thing as mgh. So ek is equal to mv squared over 2. But also, because all of that potential energy turns into kinetic energy, I can write this down that it will also be equal to mgh. So then if I apply that, ek will be equal to, in this problem we're looking at 3 times 60 times 9.8, 3 times 60 times 9.8, and that's 1764 joules. And from that kinetic energy we can find what the value of speed is. So v, so we know that ek is equal to mv squared over 2. V is equal to square root 2 times ek over m. And if you substitute and calculate, you'll find that the speed will be equal to 34 meters per second. So that's question number 3. Swiftly on to question number 4. Question number 4 is essentially the same principle, where we have a body at point A, 50 meters above the ground. So let's draw it again. Body at point A, 50 meters above the ground. So our height here is 50. This is point A, and we have that body, and it's at rest. So it will have some potential energy, and also its kinetic energy will be equal to 0. And the body is, actually I skipped a problem, didn't I? That's alright. Skip the problem, that's fine. So let's go back. I can cut it out in a second. So for question number 4, we're looking at a stone projected upwards with some speed, phi equals to 100. We're looking to find the highest height it reaches. Obviously at this point the stone has only kinetic energy because it's moving at a speed, it's not at a height. Its height is equal to 0. And at some stage later on, the stone will be over here. It will have some height, but it will have 0 speed, so it will have potential energy. Principle of conservation of mechanical energy applies again. So we end up with an equation where kinetic energy at the beginning is equal to potential energy at the very end. We get mv squared over 2 is equal to mgh. M's cancel, and height is equal to v squared over 2g, and it turns to be 510 meters. So that's solution to question number 4. For question number 5, we're looking at a body at point 100 meters above the ground. Point A, this distance is 100 meters. And we're looking to find, this is 50 meters, and the weight is 100, let me just rewrite it again, 100 kilograms, and this is 50 meters. Okay, so what is the potential energy at point A, taking ground level as 0, so obviously EP is equal to mgh, so that will be equal to, let's check my notes, 49000 joules. So then the second part of the question is, what is the kinetic energy of the body when it has fallen a distance of 20 meters? So if the body falls a distance of 20 meters, its height is then going to be 50 minus 20, which will be equal to 30. And So that's the first thing to note. Then the second thing to note will be that mechanical principle of conservation of mechanical energy still holds. So we get that EP will be equal to, so that's our original potential energy, will be equal EP2, so that's height of 30 meters plus EK2. So we can rewrite this that kinetic energy EK2 will be equal to EP minus EP2. So we subtract potential energies, that will give us the kinetic energy at that height. We can substitute EK will be equal to mgh minus, that's the original height of 50 meters, minus mgh2, that's the height of 30 meters. Or we can substitute that, take the common factor out, mgh minus h2. Now h minus h2 is just 20 meters, mg times 20, and then we can substitute that and we'll get a result of 9,600 joules. So that's our answer. For question number 6, we're looking at a pendulum. Pendulum is a specific case. When a pendulum is at its first disposition from its rest position, let's say pendulum would be hanging, this would be its rest position, kind of down here, somewhere over here. The pendulum swings through its rest position and then goes back up. This distance between the vertical distance between the position at which the pendulum starts and its rest position, or the fastest speed position, let's call this distance h. We know that distance is equal to half a meter in this case. So again, it's simple calculation involving conservation of mechanical energy. At this time, pendulum only has potential energy, no kinetic energy, because speed is equal to 0. At this stage, it lost all its height, so potential energy will be equal to 0, and it will have some kinetic energy. So we know that the sum total of those two energies has to be equal to sum total of those two energies. If we get rid of zeros, we end up with EP is equal to EK. Potential energy at the beginning has to be equal to kinetic energy at its fastest. Substitute values. mgh is equal to mv squared over 2. m's cancel. So gh is equal to v squared over 2. And we want to find speed out of that. So v squared is equal to 2gh. v is equal to square root 2gh. Not 96, but gh. Let me just write a little bit more clearly. So if you sub the value and do the calculation, 2 times g times 2 times 9.8 rather. Yeah, I know what I'm putting now. 9.8 and times 0.5. Put the values in and do the calculation out. You'll find that the speed is 3.13 meters per second. So that's for question number 6. Now question number 7 is a little bit more difficult, but it's exactly in the same vein. So let's do question number 7 now. In question number 7, we're looking at a very similar situation where we have pendulum starts swinging at some height above its lowest position. So that's where the pendulum would be hanging if it wasn't deflected. Over here, we know a couple of things now. We know that pendulum is deflected. We know that the height between the lowest pendulum position and its current position, let's call that height h. So this is this distance here. I'm going to call it h. Now, what we need for this question is the following. We need to note that this triangle, right, this one here, is a right angle triangle. Let me maybe erase the red line over here and draw it again. So this triangle, that's a crucial point. This is a right angle triangle. This is a right angle. We also know that this angle over here, we have a value given of that, and this is 40 degrees. So now, the distance, the length of the pendulum, I'm going to call it r, and we know what r is. It's 2 meters. is the hypotenuse in the right angle triangle. And you can note that I'm going to call this distance here, I'm going to call it L. So distance from top of the pendulum to this point, I'm going to call it L. Note that cosine of 40 degrees is the same as L over R. But this is not really what I'm looking for. What I'm looking for is this height. So take a look at this. Height plus the length, L plus H, height plus the length is equal to the radius. It's equal to the length of the pendulum, which I'm going to call R, is equal to R, the length of the pendulum. So if I'm looking for H, what I need to do is just subtract R minus L. So all I need to do next is to discover what L is. But I can discover what L is from this particular identity, because L will be the same as R times cos of 40. So R cos 40, that's my L. So now I can start solving my questions. We know that height is equal to R minus L, so height will be equal to radius minus radius times cos of 40. So I'm going to take the common factor out, so that will be R1 minus cos of 40. Cos of 40 degrees, obviously. So now this is height, this is my height. And I can substitute for R, that will be 2, 1 minus cos of 40. And in that case, H will be equal to, if I take a look at that, 0.46 meters. So now I know that height is equal to 0.46. The rest is simple, because all I need to do is apply the principle of conservation of mechanical energy, which tells me that mgh, so potential energy at the very beginning of the swing, is equal to the kinetic energy at the very end of the at the fastest position. Masses will cancel, so then masses will cancel, and I can find what my speed is. V is equal to square root of 2gh multiply across by 2, and then take a square root of both sides. And if I substitute in and calculate it out, I'll end up with speed equal to 3.03 meters per second. And that's the answer. The key thing in this problem, and I can't stress this enough, is to recognize the fact that this triangle is a right angle triangle, and that we can use a cosine of this angle here, of the angle between the pendulum and its rest position, let's say. We can use that to calculate the length L, and then following that length H. So this is the key thing for this particular problem. Now, moving swiftly on to problem number 8. Question 8 and question 9 are looking at the combination of conservation of momentum and conservation of mechanical energy. So for question number 8, we're looking at a mass traveling at some speed, and it collides with another mass which is at rest, and afterwards both masses join together and travel at a speed. So let's call this one 1, this one 2, and then 1 and 2 are traveling together. This will be my u1, u2, and this will be v1, the speed after the collision. Obviously, because this is at rest, u2, the speed before the collision for the second object, is equal to 0. I'm going to write down my principle of conservation of momentum. Mass times initial speed plus mass times initial speed for the second object has to be equal to the same as the momentum afterwards. Obviously, the question tells us that two masses stick, so I get m1 plus m2 times v1. Let's find what v is, because in this question we're looking for the speed after the collision, velocity rather, after the collision. So v1, divide both sides by m1, m2, noting that this is equal to 0. So I end up with just this term, m1 u1, all divided by m1 plus m2. And if I substitute the values in, I will discover that my speed is equal to 12 meters per second. So then I can continue on and calculate the second part of the question, which is the loss in kinetic energy. The loss in kinetic energy will be associated with sound that generated during the collision, and also some heating of the atoms and molecules that are forming the molecular and crystalline structures of the two solids. So loss is the same as initial kinetic energy minus the final kinetic energy. So initially only one object was moving. The mass of that object was 10 kilograms. The velocity of that object was 30 meters per second divided by 2. And at the end, both of those objects were joined together. So we have its mass at 25. And those two objects were traveling at 12 meters per second. Square it up, divided by 2. So then if excuse me, if I calculate it out, I'll end up with loss of energy being equal to 2700 joules. Question 9. In question 9, we're looking at a very interesting situation, which is actually applied in ballistics. So in ballistics, when people test what's the shot energy and the speed of a bullet before a collision, this is the method they use. So there is a mass hanging of some length of a wire, and there is a bullet approaching that mass at a speed. We know that speed is equal to 100 meters per second, and we know the mass of that object, we know the mass of the bullet. What we're concerned is that as the two objects stick, you can imagine that once this bullet collides with this object, it will give it a little bit of a push, and then this object will swing as if on a pendulum, and it will be raised by very small height, h, and this is the height we need to find. So obviously in this case we're going to again apply principle of conservation of momentum and principle of conservation of mechanical energy. The mechanical energy tells us that the kinetic energy over here has to be the same as the potential energy as the two objects joined together move up. So what I now need to find out is that what's the kinetic energy of this object, and what's to get the potential energy afterwards. So I'm going to apply my principle of conservation of momentum to find the speed after the collision. The reason I wrote this as a sum is because objects stick after the collision. So we're looking for what my speed v is. This goes to 0, obviously, because the second object is at rest. So and if you substitute the values in, you'll find that the speed is equal to 0.1198 meters per second. So then we can use that solution to find the height to which the two objects will raise. So now the kinetic energy of the two objects together, let's call it mv squared over 2, will be the same as the potential energy once the motion of that object is stopped at some height h. Let's call it mgh. You probably can note that we can cancel the two m's. So cancel two m's, and we want to find what h is. So h will be equal to v squared divided by 2g. Substitute values in, we'll find that the value of h is 0.00073 meters. In centimeters, it's 0.0. Centimeters start here. So this is meters, tenth of a meter, hundredths of a meter, which is a centimeter. So 0.073 centimeters. Not quite a lot of height at all. Okay, so hopefully this was useful. If you have any questions about any of those solutions, let me know. And hope this was of any benefit to you. Now, thank you.